Welcome to Foundations of GEM, Episode 15, Macromolecules, Folding Without Friction. This is a study version of Series 3, Episode 15, focusing on how macromolecules fold and persist. We move from small molecules with local bonds to macromolecules existing in moving landscapes. The core question becomes, can a moving landscape hold together? We ask how many bonds form large dynamic structures. Folding is not just a shape problem, it's a friction minimization problem. Macromolecules have many degrees of freedom. The challenge is to find a family of shapes that can persist while remaining useful. A macromolecule is not a static sculpture. It's a dynamic coherence volume. Its function relies on controlled motion. Proteins, receptors, and motors all require a balance of stability and flexibility to operate effectively. The total folding cost includes various elements: bond stretching, angle distortion, torsional twisting, internal contacts, and interactions with the solvent and surrounding medium, including friction. Most theoretical shapes are too costly. The structure that survives must pass the filter of admissibility, meaning the total cost, Ftotal, must be less than a critical cost, Fcrit. Biological form is fine-tuned by depth, stiffness, and viscosity. These properties enable fold tolerance, maintain fold identity, and control fold recovery, crucial for absorbing energy and preserving memory of shape. A useful macromolecule occupies a functional basin of nearby admissible conformations. Its conformational cost includes structural cost and frictional cost of movement. Function requires motion. Misfolding is persistence in the wrong basin, acting as a friction trap. A misfolded state can hold, but this persistence alone is not health. It may expose surfaces or aggregate, leading to further misfolding. No macromolecule folds alone. The environment actively participates in the admissibility landscape by shielding electrical charges, enabling hydrogen bonding, punishing hydrophobic surfaces, and helping explore conformational space. 4 key strategies for persistence are seen in biological systems: DNA with controlled access, RNA with flexible function, proteins with shaped action, and membranes with bounded exchange. The evolution of coherence progresses from bonds sharing local curvature, to macromolecules with controlled flexible structure, to cells with bounded gradient shielding, and finally to minds with recursive coherence across time. Macromolecules are the first great organic web. Folding is the search for an admissible basin, where the molecule can remain coherent while doing work. Is biological form built by design, or filtered through coherent folds?